Hello, my name is Emily Ireland, and this is my Lab 3 on circuits for Physics 2. The purpose of this lab is to predict the behavior of circuits and measure currents using an online simulation. The system is the circuit, and the surroundings are everything else. So some important concepts for this lab were the node rule, which states that current flowing into a node must be equal to the current flowing out of a node, and this is related to the concept of charge conservation. Additionally, we have the loop rule, which says that the sum of all the electric potential differences around a loop is zero, and this is related to the conservation of energy. And finally, we have Ohm's law, which is a current through a conductor at 2 points is directly proportional to voltage across those 2 points. So part 1, prediction of the results. We have total resistance 47 ohms plus 100 ohms, and we add those together to get 147. Then we have the formulas. V equals IR, and so therefore I equals V divided by R. Sorry for the extra noise. Those are some dogs I'm watching. I equals 3 volts divided by 147 ohms, which is 0.02 amps. And the circuit does as is expected, and the ammeter shows 0.02 amps. And what happens if it's reversed? The current has the same magnitude but is negative. Part 2, we replace an ammeter with a voltmeter. What happens? The voltmeter reads negative 3 volts and the ammeter reads 0 amps. Hey. The ammeter reads 0 amps because the voltmeter has very high resistance, so it becomes like an open circuit. The voltmeter reads negative 3 because there's no other voltage drop. Part 3, the voltage drop. So as you can see below, I've written out some important formulas. So the current, I equals 0.02 amps, and then we have the loop rule. So the potential at B equals the current with resistance 47 and the current times resistance at 100. And then the other following potential difference formulas that equal 0 volts in the voltage in the circuit, which as you can see follows the loop rule. And this is the graph. The graph shows voltage gain and drop throughout the circuit. Batteries cause voltage gain, resistors cause voltage drop. The sum of the voltages is 0 due to the loop rule. So the total change in electric potential is 0. So, unlike the voltmeter, the ammeter has low resistance, so current will go through it instead of the 100 ohm resistor, hence the 0.06 amps showing. It shows 0.06 because the total resistance is lower to 47 ohms, and 3 volts divided by 47 ohms is 0.06. So for the resistance of each element, we have V equals IR, so R equals V divided by I. And as you can see, I did that for each resistor and got 102 ohms, 48 ohms. And then for the wire and the ammeter, I got 0 ohms for both. So for the second part of the lab, it was RC circuits. So discharging and charging. Discharging, the light started bright and faded out. It takes around 10 seconds for the 10 volt bulb to go out. And charging had the opposite visual but also took 10 seconds. So the linearization for RC circuits is delta ln V over V initial versus time. So the graph prediction is a downward slope, which is inversely proportional. The predicted RC value is 30 ohms times 0.2, which is 6. And the experimental value is 1 over the absolute value of the slope, which is 6.88. The possible sources of error for this experiment were human error, which could have been errors in calculations or in timing, which may have altered the results, and simulations. Simulations aren't accurate to what would happen in the real world, although they do show an idealized version of it, which may be more exact, but not true to the real world. So for our what if questions, the idealized simulation predicts the capacitor charging instantly, and this is not the case in reality, Because of the emitter having resistance and other factors, the simulation does not actually represent the real world. And for the same concept for the second question, simulation is idealized and doesn't account for real-world situations, so the capacitor would likely take longer to charge in the real world than it did in the simulation. So thank you for listening.